Have you ever gone to the beach and noticed the sand is extremely cool in the morning and hot in the afternoon, while the temperature of the water doesn't seem to change at all? Both are subjected to the same amount of energy from the sun, but the different properties of water and sand cause them to react differently. One of the reasons for this phenomenon is that water has a much higher heat capacity than the sand, which simply means that it takes much more energy to raise the temperature of water than it does for sand. To understand heat capacity, we must first understand heat. When we talk about heat, we're often referring to whether an object feels hot or cold. This is because heat is actually a form of energy that flows from objects of higher temperature to those with lower temperature. So, if I touch a hot coffee mug, the mug will feel hot because the energy from the mug is being transferred to my cooler hand. Similarly, if I pick up a glass of ice water, the heat from my hand is flowing into the glass, making the glass feel cold. Internal energy is the sum of kinetic and passive energy within an object compared to an object at rest. We already know that heat refers to the transfer of energy due to a temperature difference between objects. Thus, an object can contain internal energy, but it cannot contain heat. Since heat is a form of energy, the SI unit for heat is the joule, J. Heat is commonly noted as Q in equations. Heat capacity, C, is the amount of energy needed to raise the temperature of a specific substance by 1 degree Celsius. Heat capacity can also be viewed as the ratio of the amount of energy transferred to an object and the resultant temperature rise, delta T. C equals Q divided by delta T. The heat capacity units are joule divided by degrees Celsius. Because the heat capacity of an object is dependent on the mass of the object, heat capacities are often given per 100 grams to allow for a comparison between objects of equal mass. Let's revisit our example of the temperature of the water and sand at the beach. We'll assume that the heat capacity of water is 400 joules divided by degrees Celsius, and the specific heat of sand is 80 joules divided by degrees Celsius. Let's calculate how much heat, Q, is required to raise the temperature of the sand and water by 5 degrees Celsius. Since we're interested in Q, we must first rearrange the equation. For water, Q equals 400 joules divided by degrees Celsius times 5 degrees Celsius equals 2,000 joules. For sand, Q equals 80 joules divided by degrees Celsius times 5 degrees Celsius equals 400 joules. As you can see, it takes much more energy to raise the temperature of water by 5 degrees than it takes to raise the temperature of sand by the same amount. The temperature change of an object is also highly dependent on the mass of the object. Often, a more useful coefficient is the specific heat, C, of an object, which is the heat capacity of a substance per unit mass. Experiments have shown that the heat transferred is directly proportional to the mass, specific heat, and temperature change. Q equals m times C times delta T. Returning to our beach example, the huge mass of water in the ocean is yet another reason why so much energy is required to change the temperature of the ocean water compared to sand on the beach. Understanding the transfer of heat and how different substances behave during this process is a key concept in the field of thermodynamics. Heat is actually a form of energy that flows from objects of higher temperature to those with lower temperature. The heat capacity of an object can be thought of as how thermally insensitive a material is to the addition of heat. Heat capacity, C, is the amount of energy needed to raise the temperature of a specific substance by 1 degree Celsius. As we learned, water requires more heat to raise its temperature, which is reflected by a higher heat capacity. Finally, since the heat capacity is also dependent on the mass of an object, specific heat is a value that represents the heat capacity per unit of mass. The specific heat, C, of an object, which is the heat capacity of a substance per unit mass. In the future, when considering why objects respond in a certain manner to the addition or subtraction of heat, remember that this reaction is due to both their mass and their individual heat capacity.